Okay, welcome to Unit 5, Lesson 1, Simplifying Higher Order Roots. And you'll notice it says roots/radicals, and we are using those words synonymously. Now, we've just come off a unit on polynomials where we've used the word root, talking about the x-intercept and synonymous with the word 0. And now we're using it in a different context. So I just wanted to make sure that I pointed that out to you at the beginning so that you're not thinking like, what do you mean simplifying an x-intercept? What does that mean? Well, not much. We are using it synonymous with the word radical, okay? And teachers as well as like college professors or different high stakes testing places might use either word. And so we just want to be really clear on our vocabulary at the outset. So a great place to start with this is with something that we already know. That's always a good place to start launching into something new, is to go back to like, what do we already know about this topic? Because we know that math is consistent. We know that principles carry from one area over to another area. And so if we can go back to something we're already familiar with and study the principle in a little bit more detail, then it becomes easier to extend that into a new application. So recall that a square root. So this right here is our square root. Okay. Recall that a square root undoes squaring. That is literally what it does. Now, a lot of times I will hear students say that a square root undoes multiplying, and that's a little bit too broad. We would say that division undoes multiplying, and a square root is not division, and I do want to be really clear about that at the outset as well. A square root symbol is going to have this like hook on the end of it, which in this lesson, we're actually going to put something in, like kind of wedge it right into the hook there. A division symbol, like long division, looks like that, and there is no hook on it. Now, I have seen students get this wrong. I've actually seen teachers get that wrong. And so I do understand if that's been a little bit of a point of a confusion. Maybe you thought they were the same symbol, but a square root specifically undoes squaring, which is a very specific kind of multiplication where you are multiplying something by itself. Now, the square root has an implied index of, and this might get a little bit confusing to you because you might not have seen this before, but it's got an implied index of 2. Now, I want you to, well, and here's what we mean by that. We mean that there is an implied 2 wedged into the little hook there. Okay. Now we don't normally write it. So if you do not see any kind of symbol in your root or radical there, then you assume it is a 2 and you assume it is a square root. Now, where does that 2 come from? Well, it comes from this right over here where you've got 5 squared. And remember that squaring raises something to a power of 2. Therefore, a square root undoes the squaring. And so that little 2 is just telling you this is what it undoes. It's called a square root. Okay, now just to get a handle on what we're talking about here, suppose you have a 5 and then you square it. Well, you would get 25. And therefore, the square root of 25 is 5. And so what I want you to notice is that the two operations undo each other, leaving us back where we started. Okay, take a moment and let that sink in, because understanding what these operations are and what these symbols do is just essential for being able to extend it. So you just don't want to say, well, square root of 25 is 5 because somebody told you that was true. The reason the square root of 25 is 5 is because this square root, which of course I'll reiterate has an implied little 2 in there, okay, is undoing the squaring. So you have this operation of squaring, and then you can undo it with a square root, and you end up back where you started from. Okay, so that's something that we already know. So let's take it one step further. We have talked considerably about cubing. Hopefully you've seen cubing in your geometry classes. So to undo cubing, we use something called a cube root. Okay, which think about that vocabulary wise for a second. Should make sense. You take something, you cube it, and you can undo it with a cube root. Now the symbol for a cube root is going to be that radical or that root again, except this time in that little hook there, we have a 3. Okay, and that tells us that this is a cube root. Now that little number there, I tossed that vocab out on the previous slide, is called the index. Okay, so it's called the index of the root or the index of a radical. So back to the title of the lesson, when we said this lesson was about simplifying higher order roots or radicals. This is what we're talking about. We're talking about something higher than a square root, like a cube root. Okay, now let's just illustrate what we mean by this. So suppose you have the number 4 and you cube it. Now keep in mind what that means. That is 4 times 4 times 4. And you get the number 64. Now suppose you wanted to go backwards. Okay, so you wanted to take the 64 and go back to the 4. The way you would do that is with a cube root. Now, I want to make sure that I point out a couple things before we go any further with this, that your index needs to be smaller and it needs to be written in or just above the little hook on your radical symbol. If you write this, that is not the same thing as this, okay? So take a moment, pause the video if you need to, make a little bit of an extra note. This means take the 3 and multiply it by whatever is in your radical. This is the index and it indicates the type of radical. So this one, the 3 is floating outside. That makes it a coefficient and it makes this a square root, because remember, if there's no number written, then we assume it is a square root. And this is actually changing the kind of root it is. Now, I do have to say, with some calculators that do higher order roots, when you type it in the calculator, the calculator doesn't have the display capabilities of writing it like this, and the calculator will write it like this, and it'll often indicate it with like a little X up there, and that will be the little X up there. That's an X, okay. And that'll be the calculator's way of saying the X is equal to a 3. It's not the best notation, but it is just due to the limitations of the display on the calculator. If you are writing it out by hand, it needs to be written out correctly. All right, so now let's generalize. So we go back to square roots. We kind of review what do those mean. Then we extend that to cube roots, because we're pretty familiar with cube roots at this point, or cubing. Now we want to generalize it, because math is really good like that. So if you get how a square root works, it doesn't take too much to take that to the next level. So to generalize it, we would say that the index, that is that number that's in the radical there, indicates what the radical or the root undoes. Okay, so if a square root undoes squaring and a cube root undoes cubing, then if you saw a higher number in there, like a 4, a 5, a 6, a 7, a 10, a 100, okay, then that just tells you what it undoes. It undoes raising something to that power. So we have over on the left here a couple of examples. The square root of 4 squared. Okay, now keep in mind, square rooting undoes squaring, so that's going to leave us with a 4. And we don't typically write the little index of 2 in there, but there is an implied index of 2. It's like really hard to do that on my screen. Okay, so that is square root undoes squaring. A cube root undoes cubing. So if you look at that and you have 2 to the 3rd power, and then you take the cube root of that, well, you know the cube root undoes the cubing, and that's going to leave you with a 2. And now just generalizing that, let's say we have a 4th root. Now, most of you have never seen this before, but the principle is the same. So if you have 7 and you raise it to the 4th power, and then you want to undo raising it to the 4th power, then you would take something called the 4th root. Okay, and so that would bring us back to the 7. Incidentally, it also works the other way around. So if you took a number like 7 and you took the 4th root of it, and then you raised it to the 4th power, that would also undo it. Okay, because they're what are called inverse operations. So just like we would say division undoes multiplication, but we could also say multiplication undoes division, or adding undoes subtracting, and subtracting undoes adding. This works in both ways as well. So the root radical will undo the exponent, and the exponent will undo the radical. Both directions will work. Okay, so here's our strategy for simplifying any root or radical. And this is a great strategy. Now, ultimately, I don't want you writing out all the steps that I'm going to show you in this strategy, but it's okay to write them out for as long as you need to. So I want to make that distinction between like work that you have to show versus work that is helpful to show, but not necessarily required for you to do in order to demonstrate that you understand a concept. So this strategy, we get what's called the prime factorization. And that means we factor our expression into prime factors. That means things that cannot be factored any further. For the variables, this is really easy. For the numbers, it might take a little bit of scratch work off to the side. So we're going to get the prime factorization of what's called the radicand. Okay, now that's just threw some vocab out there. The radicand is the thing under the radical. Okay, now, and then find groups of a size that matches the index. And the reason we want to do that is because the index tells us what the radical undoes. So if we can find groups that match that size, then we know the radical will undo them. So if you think back to the previous slide, which I cannot go back to, but like the 4th root undid 7 to the 4th. The cube root undoes 2 to the 3rd. A 6th root would undo 10 to the 6th. Okay, so you're going to look for groups of that size because that's what the index is going to tell you. Well, that's what the index tells you the radical undoes. So here's an example. Now this might look kind of scary, but it's not. I promise you it's not. This is a good, solid strategy. The variable part is going to be very simple. It's the 54 that is going to cause us to trip up a little bit. So if you struggle with the 54, we'll just set up a little bit of space over here. This is some scratch work. So you can do this on the desk. You can do this on the margin of your paper. If you can do it in your head, you can do it in your head. And you'll probably need a calculator. So I've got my cell phone here. And what we're going to do is break down that 54. So right off the bat, I know that 54 is an even number. And so I'm going to divide it by 2. And then you might need to use your calculator to figure out what that is. So 54 divided by 2, and that gives me 27. And now from here, I'm okay. Now you might need to do a little bit of work here, but you might recognize that 27 is 3 times 9. And so the 27 breaks into 3 times 9, and the 9 can break down even further into 3 times 3. So once I get it right here, 2 times 3 times 3 times 3. That's what's called the prime factorization. Even if you start your factoring a little bit differently than that, everybody should end up at the same spot because that's the prime factorization. There's only one way to get prime factorization. That might take a little bit of work. It might take grabbing your calculator. That's going to vary from person to person. So over here on the left, I know that's going to be freaky for a second. It's very long, but it's going to come out really nice. So the 54 is 2 times 3 times 3 times 3. X to the 3rd is x times x times x. And y to the 5th is y times y times y times y times y. All I did there was I just dumped that expression out. And now I'm going to look for groups of the same size as the radical, or as the index. So the index on this radical is 3. And so that means I am looking for groups of 3. Here's what I mean by that. Here's a group of 3. Here's another group of 3. I got 3 3s. I have 3 x's. And here I have a group of 3 y's. And I'm looking for those groups of 3 because that means it's raised to the 3rd power. And what do I know about the cube root of things raised to the 3rd power? Well, I know that they are equal to the thing that was raised to the 3rd power. That was a little bit awkward how that came out. So for instance, I know that the cube root of 3 to the 3rd power is 3. So this piece right here, where I'm doing the cube root of 3 to the 3rd power, that simplifies to just a regular old 3. I also know like the cube root of x to the 3rd power. Well, there's no reason to think that it should be different for an x than it is for a number. So the cube root of x to the 3rd power must just be x. And then I can do the same thing with the y. The cube root of y to the 3rd power is just y. And those things no longer have the radical over them. If you look carefully at this, okay, once I do the cubing and the cube root, there's no more radical. It's just a regular old 3. It's just a regular old x, and it's going to come outside. Now we need to look at what is still underneath our radical there. Well, I still have a 2 that's underneath. And way down here, I have y times y, which is y squared. And we're done with the problem. Ta-da! Hopefully not too bad. Now, some of you might be thinking, well, what if I can find a faster way to do that? Like, for example, why did you take x to the 3rd, break it all up, only to put it right back together again? You would have a great observation there. That is not necessary. Now, I will do that for consistency when I'm demonstrating how to solve the problems, but if you are able to see that faster and you're like, I don't need to expand out the x to the 3rd, that's totally fine. Feel free to skip that. Remember, some of this work ultimately we wouldn't want you to show, but you can show it for as long as you need to. Okay, so as you start to make some connections there, you don't need to show all this work out. So here we have the 4th root of 81 x to the 4th y to the 8th. So let's go tackle, let's go tackle that 81. 81 I know is 9 times 9. And then each of those 9s can break into 3 times 3. So there's my number. So here we go. Now this will look really long and scary, but only for one line. So don't get too caught up in that. We have 3 times 3 times 3 times 3 times 3. X to the 4th is x times x times x times x. Y to the 8th, ouch. 1, 2, 3, 4, 5, 6, 7, and 8. And typically what I will do as soon as I'm done with that is I will do a quick count. 1, 2, 3, 4, 5, 6, 7, 8. Just because when you're writing that many out, it can be easy to miss one, and we don't want to miss one. Step number 2, here we have a 4 as our index. So this is a 4th root, and what it undoes is 4th powers. So we're going to be looking for groups of 4. Here's a group of 4. So if I had the 4th root of 3 to the 4th, that would just be regular old 3. Here's a group of 4. The 4th root of x to the 4th would just be x. Here's another group of 4. The 4th root of y to the 4th would just be y. And then we have another group of y's. The 4th root of y to the 4th is another y. Now, most of us would not write 3xy. That's a little bit silly. We would write 3xy squared. And you'll notice in this one that the radical is no longer there because we were able to do the whole problem. Now, there are other ways to do this. So if you like scrounge YouTube or if you decide to photomath it, I'm pretty sure photomath will do something very different. I think photomath will use laws of exponents and break like the y to the 8th into y squared raised to the 4th power. So there are other ways to do that. As always, don't copy Like, just don't copy stuff that you don't understand. So this is a great strategy. It brings it back to the basics. If you do understand other strategies, that's fine to use them as long as you are showing the work. All right, now example 3. This strategy also works for square roots in case you've struggled with this in the past. So if you've had trouble with square roots, simplifying them, and your classmates are able to get these answers, you're like, I don't know where they came from. Okay, you can also use this strategy for square roots, and I wanted to make sure that I did show you that. So taking a look at the 8 would be 2 times 4, and then you can factor that 4 into 2 times 2. And so 8 is 2 times 2 times 2, which we've seen before because we've looked at 8 is a perfect cube. Okay, so over here we will have 2 times 2 times 2, and then x times x times x, and then 6 of these, 1, 2, 3, 4, 5, 6. If you don't see an index, it is assumed to be a 2. So with a square root, we are looking for groups of 2. There's a group of 2 2s. So the square root of 2 squared is 2. Here's a group of 2 x's. The square root of x squared is x. Then I have a bunch of groups of y here. Okay, we're looking at groups. Now I have 3 groups. So some of you might go, okay, that's y times y times y. Now most of us don't write y times y times y. We would say y to the 3rd. And then see what's left underneath. So we're still left with a 2. We are still left with an x. And we're done. Ta-da! Okay, pause the video. As always, one of the advantages of working with a video is that you can pause it. So if I went through something a little bit too fast, you can go back and rewind it. You can take your time copying this over into your notes, and you absolutely should be writing this down so that you have examples. And also write down anything I might say that you think would be beneficial. So here we have some practice problems, and I have their use separate paper if needed. So in class, we will pause and work these out individually just to get some practice with the process with this. And I will work them out. So pause the video, work them out, and then I will review them in the video, probably like doing a problem and then erasing it. So so pause the video and work them out first. Okay, so that first one, ouch. Now the thing about I'm saying ouch about it isn't because the problem's hard, it's just because there's a lot of stuff in that problem. So for that first one, we have the cube root, and then we have to break the 20 down. So 20 I know factors into 4 times 5, and 4 will factor into 2 times 2. So that would be 2 times 2 times 5. Now even if you said, oh, it's 2 times 10, yes, and then 10 breaks into 2 times 5. So no matter how you start that problem off, you should end up with 2 times 2 times 5. Then we have 4 x's and 5 y's, and then 2 z's. Now we haven't dealt with z's too much this school year. I do cross my z's. This is a cube root, so we are going to be looking for groups of 3. I don't have any number groups of 3, but I do have some x's and I do have some y's and nothing else. So what am I left with under my radical? Well, the 2 times 2 times 5, I guess I can put it back together again. Now, some of you might, when you're going through the factoring process, realize that you don't have a group of 3 and you never bother taking it apart. Okay, but we'll go ahead and put the 2 times 2 times 5 back together again. I have 1x, I have 2 y's, and I have the 2 z's. So hopefully you have something that looks like that on your page, but if not, go ahead and make a correction as needed. Second problem. is the square root of 20. So I like doing this one because we do have a lot of students that do struggle with simplifying square roots, and this does give you another tool to use. So we just did the prime factorization. We said the prime factorization of 20 is 2 times 2 times 5. Now remember, when you have a square root, it is implied that the index is a 2, so you're looking for a group of 2. The square root of 2 squared is just a 2, and what's left under the square root is a 5. So that simplifies into 2 root 5. You might hear 2 root 5, 2 square root 5, 2 times the square root of 5. You could hear 2 radical 5. Okay, so there's a lot of different ways you might hear that presented verbally. That leads us to our last problem, which is the fifth root of 10x to the fifth, y to the seventh. Now, some of you are already getting to the point where you're like, okay, the fifth root of x to the fifth is x. I don't need to take the x's apart. Or you could say, well, the fifth root of y to the seventh, 5 of the y's are going to come out, and I'm going to be left with 2. And you start noticing these patterns. Totally 100% okay. You do not have to show out that prime factorization as soon as you are comfortable not showing it out. Do it for as long as you need to. 10 factors into 5 times 2. Then we have 5 x's and a whopping 7 y's. And it is a fifth root. So we're looking for groups of 5. Don't fall for pulling that 5 out. You're not looking for 5s. You're looking for groups of 5. And we don't have any groups of 5 with the 5 and the 2. We do have a group of 5 with the 5 x's. And then we also have a group of 5 with 5 of the y's. Everything else is still going to be stuck in there. So 5 times 2 is 10. We got all of our x's out, but we still have 2 y's down at the end there. Okay, so be careful with that. A lot of students will kind of get like confident and start to jump over to, oh, like the 10, I can take out a 5 and I'm left with the 2. No, you're looking for groups of, because the radical undoes multiplication. So you have to see like 5 5's multiplied together in order to take a 5 out. Okay, that's a common mistake. If you made it, it's no big deal because this is practice, but do pause the video and make those corrections in the work and any notes that you need in the margins to help you remember that in the future. Now, there are a couple of catches, and by catches, I just mean things that you need to be aware of. Now, I want you to recall what happens when we take the square root of a negative. Okay, so if we were to look at the square root of negative 8, we could break that into 2 times 2 times 2, just like we would in the previous problem, but we'd also have to have that negative 1 out there. Now, we could be looking for groups of 2, which is fine. So we would have 2, but also remember that that square root of negative 1 is going to be equal to an I. And so that's going to be able to come out with the square root, and then we're left with a 2. So the square root of negative 8 simplifies into 2i root 2. And I just want you to remember and notice that we do end up with an I in there. So when you're taking the square root of a negative, that's when those i's pop. So what does this mean if you're taking a root of something higher than a square root? What about a cube root or a fourth root or a fifth root? Do you still end up with those i's? So let's take a look at RSVP rechoice. Oh, I have to RSVP to something. My phone just set off a notification. All right. Okay, so let's take a look at a cube root. The cube root of negative 8. Now, there's a couple ways you can do this. This gets a little tricky. So somebody might say it's negative 2 times 2 times 2. Okay, and then you kind of come to a standstill because then you don't have a group of 3. You've got 1 negative 2 and 2 2's, and you're like, I guess I can't simplify it. But that shouldn't sit quite right because you know that 8 is a perfect cube. So it seems like if you're taking the cube root of something that is a perfect cube, you should be able to go somewhere with it. Watch what you can do. you can actually make those all negative 2's. Okay, so just kind of to get this, so that would be negative 2 times negative 2 times negative 2. Well, negative 2 times negative 2 is positive 4, and then positive 4 times negative 2 is negative 8. Okay, so you could think of that as negative 2 times negative 2 times negative 2, and now you've got your group of 3, and you just have negative 2. Okay, so that, now you might be thinking, well, I would have never thought to have done that. That's why you sit in a class and have a lesson. so you can kind of be aware of that. Now, what does that mean? How can you apply that? What that means is that we can take odd powered roots of negative numbers. So the i's show up, okay, whenever you have even roots, like a square root or a fourth root or a sixth root and so forth. That's when you're going to have those i's show up, because of the number of times that you're multiplying something in. So if I were to put like another negative 2 up there and say negative 2 to the fourth power, then we would end up back at a positive. But if it's an odd number of times, so you're multiplying it in 3 times, 5 times, 7 times, then you can end up with a negative number, which means that you can take the negative, the root of the negative, and you'll just end up with a negative number. Okay, that can be a little bit tricky. So that's why we have a special little blurb in the lesson about it. One more. Okay, this one bothered me so bad. I think the year I was in pre-calculus, this just bugged me. We just kind of get into some of the formalities with the definitions that we use. So follow the reasoning here. If x squared is equal to 25, what does x equal? I'll give you a moment to think about it. Okay, x could be equal to 5, or x could also be equal to negative 5. And a lot of times we would write that as x is plus or minus 5, because both of those work. 5 times 5 is 25, but negative 5 times negative 5 is also 25. So you actually have 2 answers. However, when we take the square root of 25, we only take the 5, meaning we only take the positive one. We never take the square root of 25 and say it's negative 5. Okay, it's always the positive. Now, what that means is that when we have a variable, so something that we are not sure what the value of it is, we don't know if x is positive or negative. Okay, like think back up to that first line there. If you have a variable, you actually don't know if it's positive or negative. But if you're taking the root or the radical of it, you need to make sure that you have the positive root, because that is how we take radicals. We go with the positive. Again, this really bothered me when I was in school. I was like, well, why do we even have to take it? Because that's what we do. Therefore, we have to put absolute value around it. And we know that absolute values will take any quantity, and unless it's 0, which it won't be in this case because there'll be something there, and make it positive. Okay, so a positive, you take the absolute value of it, it'll still be positive. If you have a negative, you take the absolute value of it, then you'll make it positive. And that can ensure that we're getting the positive root. So let's take a look at some of the previous examples that we had that I don't have the answers for in front of me. They're like on another piece of paper that's in the copy room. But let's take a look at this. So this one we already did out. So we had 3xy squared. Now let's take a closer look at this. The 3 I know is positive. Good, okay? Y squared has to be positive. Think about that for a second. Y squared has to be positive because you take anything squared, okay? Or at least it's not gonna be negative. This though, we don't know. X itself could be positive or negative, and we don't really know. So the X needs to have absolute values around it. So the way you might see that written is with the absolute values, but only around the x. You might also see it like this with like the y squared out front, and that's just changing the order of it so that the absolute values are on the right hand side. That's just a formality, but we need to make sure that we're getting all positives, and there's only one thing there that we're not sure about. This was one of the other previous examples. So what is this? This was 2x y to the third, right? And then we had a 2 and an x left inside. Okay, so if we look at this, the 2 we're confident about, like that's obviously positive, but x we don't know, and y to the third we don't know. Because remember, if you think back to the last little catch in there, like if you take a negative number and multiply it in 3 times, you could still end up with a negative. So those 2 we're not sure of. So the way we would write our answer for that is we would have the 2, and then the absolute values would go around the piece that we weren't sure about, which would be the x and the y to the third. Okay, and that's just to ensure that we're getting a positive. Okay, so now that might have thrown you a little bit and you get uncomfortable with it, but I do have some good news. Okay, so we'll wrap up this lesson. When do you need this? Okay. Most of the time, remembering the absolute values is not crucial. It is not a deal breaker, like you are going to fail all your math classes if you don't remember the absolute value. It's just not. They come into play only with even powered roots. Okay, like they're the only ones. So if it's an odd powered root, you're okay because you can get negatives for that. Many teachers are not like what I would call picky about this, but you may see it on a high stakes test, so it is worth knowing. Because what I don't want to have happen to you guys is you're doing a problem and you get like 3xy squared, but then when you look at your answer choices, you see 3y squared, and then you see those absolute values, and then you get thrown off. You're like, what? The absolute values? That can't be the right answer. She never told us anything about absolute values. And so, yes, I'm telling you something about the absolute values, so that you kind of have an idea. This is why the absolute values are there, and you know that that's still the answer choice you should pick. Okay, so you can't just bail and say, oh, she never told us anything about that. Yeah, I did. But most teachers are not super picky. Now, if you are watching this video and you don't have me as a teacher this year, okay, or maybe you do have me, but it's a different year with different standards, then your teacher might be pickier about it, okay? So whatever teacher you have, you need to follow the directions for that teacher, what their expectation is. But most of the time, in most cases, this is not this deal breaker of like, yeah, you've got it, or no, you don't, and we're gonna not give you any credit. But you also need to know enough about it so that you're not freaked out or thrown off if you see those absolute values come into play somewhere. All right, so that wraps up this. At the time I'm recording this, I have no idea what your homework is, so we'll just have to stay tuned for that. As always, you know how to reach me if you have questions.